Let's look at the previous triple integral in a new coordinate system. In the last problem, we had this integral, and what I've done is written the actual solid Q for these limits of integration in Cartesian coordinates. It's very simple to actually produce the cylindrical coordinate representation, but the spherical takes a little bit more work. Now, I may add this. The extra work that's required to produce the spherical coordinate transformation is well worth the effort because the integrals that result are actually much simpler. So what we're going to do is we're going to start out with the Cartesian Q here. That is, x runs from 0 to 2, y runs from 0 to the square root of 4 minus x squared, and z runs from 0 to the hemisphere, basically, the square root of 16 minus x squared minus y squared. And I'm reminding you here about the Cartesian equivalence. That is, x is rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. Now, in order to work this problem, we have to notice that the part here, as it extends to the hemisphere, does not fully complement the hemisphere. It cuts into it, as I've written here, in a cross section. And so in this particular area from 0 to pi over 6, rho is always running from 0 to 4. But as you move into this range, from pi over 6 to pi over 2, the actual magnitude of rho is dependent upon phi here. And so that's where the difficulty is, because our region in the plane doesn't extend all the way to 4. It stops here at 2, as you well know, from 0 x to 2. So what we want to do is break this up into two pieces. So first, let's actually find this intersection here. Even though I've written pi over 6, you're thinking, where did I get that? Well, I did this computation. So now what we're going to do in the z equation, we're going to replace y with the square root of 4 minus x squared. Now when we square it, we just get 4 minus x squared. The x squared terms absorb, and we're left with the square root of 12. And that's just 2 square root 3. Now we use our equations here, our Cartesian equivalents written in terms of the spherical coordinates. We just set z equal to 2 root 3. As I said before, rho is equal to 4 in that particular area, and we have cosine phi, as we have right here, equal to 2 root 3. When you divide, cosine phi is just square root 3 over 2, and therefore phi is just pi over 6. So this defines the region from here to here. That is, remember, we measure phi starting here, 0 to pi over 6. Phi is measured from the positive z-axis. And so, again, the theta is the easy part. That's always going to run from 0 to pi over 2. Phi now will run, again, from 0 to pi over 6. And then, of course, rho runs from 0 to 4. So that's the simpler region. We're just going to call that Roman numeral 1. Now, as I said before, for part 2, the magnitude of rho varies with theta. And just as a little side calculation, you know you have the square root of x squared plus y squared. So I went ahead and computed x squared plus y squared here using these formulas. And you just get rho squared sine squared. And of course, when you take the square root, you do get rho sine phi, the absolute values, but everything's non-negative in the ranges that we're working with. So that's just a little side calculation there that we will need. Now, of course, we just do some right triangle trigonometry here. We see, of course, since we're measuring phi from the positive z-axis, this angle right here will just be pi over 2 minus phi. And so when we actually do the trigonometry, we do cosine pi over 2 minus phi is 2 over rho. And notice that I've written this right here, but this is just the cofunction identity. Cosine of pi over 2 minus phi is just sine of phi, and of course this equals 2 over rho, so we're using our pre-calculus. Sine phi equals 2 over rho, and just interchange the rho and the sine phi, you just get rho is equal to 2 over sine phi, or obviously 2 cosecant phi. So that gives us the extra punch that we need for this particular part of our integration region. So now notice, again, we have theta from 0 to pi over 2. Of course, phi will run from pi over 6 to pi over 2. And now the important part that we just figured out is that now rho will run from 0 to 2 cosecant phi. So again, what we see as we have this vertical line here, the magnitude of rho definitely does depend on the value of phi. And so now we have two integrals. We'll call this region 2 and this region 1, thinking of these solid regions. And so we take the original integral and we use our coordinates here, that is 0 to pi over 2, 0 to pi over 6, 0 to 4. And of course the square root of x squared plus y squared is rho sine phi. And of course now the Jacobian absolute value here is rho squared sine phi. We always have to use that when we're doing change of coordinates. Okay, so that takes care of region 1. For region 2, we have 0 to pi over 2, pi over 6 to pi over 2, and now of course 0 to 2 cosecant phi. And again, the same rho sine phi for the square root of x squared plus y squared and the Jacobian. So now what we're seeing here is that even though it took some work to create these integrals, you can look at these integrals and see that they are very, very straightforward. And once we actually do the second problem after this, then we will show that these integrals actually produce a value that we can depend upon. And having taken the time to do the spherical coordinates, we can actually execute integrals that are doable. And we are done.